Okay, so in this video, we will continue our revision on second order circuits, and we will now start with the non-ideal LC circuits. Before going into that, last time we saw these transfer functions. I should have had mentioned that all of these transfer functions are in particular for second order systems, but which are lossless. Why I'm saying they are lossless? Because you can see that at infinity, all of these transfer functions at resonance, all of these transfer functions are easily blowing up to infinity, right? Another catch, a giveaway was that we already discussed that the general denominator characteristic equation of a second order system looks like this. So basically, when damping in is absent, then only this S term is missing. So we can understand that these are undamped or basically lossless system transfer functions there. So that is one small thing that we can mention. Let us talk about some non-ideal AC circuits. So before going to non-ideal circuits, I think this standard term we all should be knowing is that what is quality factor. So it gives us an essence about how much energy can the circuit store and how much energy is dissipated in the circuit. Thing to remember here is that it is 2 pi times max energy stored and energy dissipated per cycle. Alternatively, the same formula can be easily translated into resonant frequency times max energy stored divided by the average power dissipated, right? So it's not exactly the resonant frequency. This guy is nothing but just 2 pi by t, where t is the time interval. So it's not really correct to say call this omega naught as a resonant frequency. Anyways, uh, now, coming to non-ideal inductor and capacitor, so we can understand that for any non-ideal inductor capacitor, it will obviously then have losses, right? And those losses will have to be modeled by resistor. Now, you can model that loss by a series resistor or a parallel resistor. That's exactly what we have tried to discuss over here. So, first of all, we have tried to just define the Q factor for a series RL circuit, and we have tried to define factor for a series RC circuit. Again, here Q factor is just as we defined earlier. It is what? It is the maximum energy that the inductor could store when here for simplicity I subjected it to a sinusoidal current input. So the max current it could store was just half times the inductor times the maximum amplitude for the current, right? Times omega naught, which is basically the frequency of the input, and divided by the maximum the power that it is dissipating in one cycle, which is just I RMS square times RS, which is I naught square by 2 times RS, and thus we arrive at this particular expression, right? Similarly, by following here, I just subjected this series RC network to input current, sinusoidal current, and by doing this calculation, we arrived at this expression for our quality factor. Yeah. Now, when talking about the parallel equivalent, again, we must understand here that in series representation, we are talking of it as LS in series with RS, similarly CS in series with RS, right? And we can equivalently express the same circuit as LP in parallel with RP. Here again, I did the derivation by keeping a voltage source in parallel, and then I basically, because it was just easy for me to do the calculation, and there we arrived at this quality factor, and here we arrived at this quality factor by a similar approach. Now, since we understand that both of these are basically equivalent, so we can basically equate their impedances, and finally the expressions that we establish are that this RP is basically equals to RS times 1 plus QS square, and this is also equal to this, which is basically true for a representation of a non-ideal inductor, and this expression is true for representation of non-ideal capacitor, and this resistance equations stands true in both cases. And again, since these two circuits are equivalent, and these two circuits are also equivalent, so the Q parallel and the Q series is basically the same. So that is the idea that we basically want to convey, that how can we express non-ideal LC circuits. Again, these derivations can be simply done by just equating the two impedances across the two terminals of this network and this network. But again, it is just some lengthy calculation which I did not really go into. It's not that lengthy, but we can derive it actually. But for the sake of saving time, we are not going really deep into it. Now let us just move on to RLC circuits. Yeah. So, moving on to RLC circuit, we should recall that in the end, all of these simple RC, RL, RLC, RLC circuits are differential equations inherently. So, we can solve them by solving the homogeneous equivalent, which gives us the complementary integral, and then taking the additional term which term which causes inhomogeneity into account into consideration, and from that we can derive the particular integral, and that's the entire solution, right? Which gives us the entire complete picture as of what is happening in the circuit. Now, this is also another important way in which we can basically express the Q factor, which is omega naught divided by the bandwidth of the circuit. Alternatively, it can also be expressed as 1 by 2 times the damping factor. Yeah. Now, this is a loose definition which I have created. It's very loose to say because here time constant does not really make any sense, right? Because it is no longer a first order circuit, it's a second order circuit. So here, basically again, the argument which or the my shortcut or my mental model that I had was the series circuit. We'll say inductor is buff and resist in the parallel circuit capacitor is the buff. Why I said that is because this tau term that I have defined it as the time constant of a first order circuit. So here we are saying that here for series we use the time constant of for corresponding to a RL circuit, and here we'll use the time constant corresponding to a RC circuit. Why so? Is because if you are defining your bandwidth can now easily be defined by 1 by tau, and what as it happens to be for this series circuit, the bandwidth is R by L, and for this circuit, the bandwidth is 1 by RC. So again, without actually having to calculate it, we can quickly derive it also, right? Again, since we know that this is a series RLC circuit, so were we to sketch the impedance of the circuit, it will look something like this, right? Where this maxima basically will occur at what? When will this maxima occur? By the way, is this impedance or admittance? This is admittance actually, because admittance will maximize for a series circuit at resonance because the imaginary components cancel out. Alternatively, the current will maximize. So we can also say that this is the expression for the current also, right? Basically, the idea is that at resonance, this will peak, and the frequencies at which this response will be 1 by under root 2 are frequencies omega 1 and omega 2, and this is the general expression for that, which again we can actually derive if we actually try to factor out the expression for the impedance or admittance rather. But again, I'm not going to the maths. This expression basically, these expressions basically stand true for both series and parallel circuits. So that's why I'm not really going into that. Again, we can easily understand that the bandwidth is what? Bandwidth is just omega 1 time minus omega 2, and again these two terms will cancel out, and then we can actually understand that what we'll have is bandwidth. Basically what we'll have is bandwidth itself, right? So so it's quite simple to understand. For large resonant frequency, this bandwidth approximately is equal to the average of these two frequencies. Yeah. Now, going in deeper into this, we already defined the quality factor as frequency divided by L by the bandwidth. And here we must understand that now when we are talking about this omega naught, here actually we are talking about this omega naught. When we are talking about omega naught, this now, here it is some general frequency, okay? Some general frequency. But when we are talking it in this representation here, this is resonant frequency, okay? That is something that I want to specify. It's very important to distinguish that here it is some any general frequency. It can be input frequency also. It typically is input frequency, obviously, and if it is since it's an LTI system, and here it is just the resonant frequency. This is something that I must mention. So now we can mention equate the Q factor as omega naught L by R, and from this we can actually derive our eta as this guy, and from this expression we can derive our eta as this guy, or basically the damping factor. Great. Now, this is the equation that we can derive for a series circuit, since we are basically finding current as the output. So here we can have this expression which we can easily establish by just applying a simple KCL, and here also by applying by simple KVL, and here by applying some simple KCL we can arrive at this equation where we are defining basically our voltage as the output. And again, we can understand for a constant input. If the input is constant, then you can understand that this guy will just vanish away to zero, and you can just solve this differential equation. And again, the solution of this differential equation also can be a wide array of possibilities, right? Similarly, the solution of this differential equation can also be a wide array of possibilities, depending upon, like we already understand that the general solution of second order differential equation for a homogeneous second order differential equation is basically what? It is EA, A1E, S1T plus A2T, E, S2T, where S1 and S2 are the roots of the differential equation, and the A1 and A2 can be derived by applying boundary conditions, right? So this is what we understand will be the general solution, or the CI, or the complementary integral. And when this term is non-zero, so that means then there we have to basically also account for the particular integral. So that is the basic idea. Okay, so here, as we already talked about, so that here impedance can be expressed as this, and it's again very simple to establish this actually, because here if you just apply Laplace transforms throughout, and you just equate this guy to zero, and you equate this guy also to zero, then you can actually, you don't even need to equate this guy to zero. Actually, it will, the Laplace of this will be just simply s times V in of s, right? So you can just easily get your admittance as this, and you can get your impedance as this, right? And now again, here you can again understand that L is in the numerator term, dividing the numerator rather. That's why I said initially that we can consider inductor as the bar in a series circuit. Yeah, and again, this expression, why this expression is good, especially the characteristic equation of this function is good for a RLC circuit in both the cases. Why I'm saying so is because now these terms are not containing any specific R, L, or C terms, right? Because if R, L, C terms would have had been present, then there would have been some difference, right? Because here it is RL, here it's RC. So this is a more general way of expressing the characteristic equation of RLC circuit. Now we can again equality express it as this guy. Now we'll understand how this representation came about. We'll understand it soon enough. Now what I'm saying is that since both of these characteristic equations are same, you can find its poles, right? It is just a simple formula that we have applied to find roots of a quadratic equation. And now we can just say that sigma, this delta d can be equal to this term, and this entire imaginary term can be equal to omega d. Now we can already understand that if we see in the root locus and we try to plot these two roots, so these two roots are complex conjugate, right? So this is basically the S plane, right? So we can understand that the real part are same, and only the imaginary part are opposite in sign. So we can understand that both of these angles are same, and so we can say that tan theta is basically equals to what? This term divided by this term, right? Now if Q is very much large, this term will be approximately equal to omega naught. So it basically is omega naught divided by this term. So this term thus is approximately equals to 2q. Now, where the minus sign vanished, someone might ask. So since this is the negative axis, right? So we can actually negative sign can also come into picture. That's not a big deal. So let us just for simplicity just say that the mod of tan theta is basically 2q. Yeah. And now that we have established this, but again, intuitively, if you understand, see since theta is an angle which is less than 90 degrees in first quadrant, so definitely tan theta must be equals to 2q, yeah, which is where q is obviously positive. So now what defines basically large q over here? So the definition of large q again is just that q should be very much large than half because because when q is equals to half, then this term basically vanishes and becomes zero. So that means that q must be large, very larger than half. Then only this term can be approximated to one, and then this omega d will be equal to omega naught, which is basically the resonant frequency, right? Now that we understand that we can express the poles of the circuit like this, now this transfer function can be this characteristic equation can be easily expressed like this. That was what I wanted to convey. So if we have this characteristic equation, it can be easily expressed in this way. And we can actually easily expand this and substitute the value of sigma d and omega d, and you will just converge at this expression only. It's not really a big deal. Again, here also, if you just apply Laplace transform and do some basic substitution of Q factor, you will easily arrive at this equation. Cool. Now, here we have just talked about impulse response to parallel RLC circuit. So here we have just applied some current input, so we would expect some voltage output, right? So here is the expression for the impedance, and this is the expression of impedance. And now, why is this helpful? As we discussed before, is that now we can easily split this term into two, right? So now that we have easily split this term into two, so we can imagine that this S plus sigma d divided by this guy is just now here what we are doing is just applying up another property of Laplace transform, which basically says that if Laplace transform of xt is x of s, then if we are finding Laplace transform of e minus at xt, then it will just simply be x s plus a. So here also we can understand the same thing because now we can understand that this entire term is just the Laplace transform of e minus e to the power minus sigma d times t cos of ut, right? So that is what we obtain by taking its inverse Laplace transform. And this term basically now will yield us a sinusoidal term. So this is what we got times ut, and this guy also will stay outside because of this factor. And then this can be just further simplified, and this is the expression which we get, which is basically a decaying sinusoidal term, right? Again, these two terms can easily be merged, right? Because since two uh, sinusoids are adding, so basically we'll get some equivalent amplitude and some equivalent phase. So that's what we did. It's some standard maths, so I won't really discuss it much. It's something which we have been doing since childhood, right? Again, when q is much greater than half, then basically this expression can be just be equal to 1 by 2q, and thus this expression of V out will converge to this, right? So again, just to remind, as a reminder, we are finding the impulse response. That is why this impedance response easily translated into our V out, right? That's just a reminder. So this is the expression of V out we get. And again, since we can understand that this E minus sigma dt, basically this term depends on sigma d, which is inversely proportional to q. So again, here we can intuitively understand that for larger q, the decay will be less, right? Which means that this sinusoidal oscillation that we are having, decaying, which is decaying with time. If q is large, this decay will be less, and this amplitude will decay less and less, right? And this envelope will be basically a decaying exponential. Great. So now that we understand this simple RLC circuit also, we can discuss more things, that is estimating Q from impulse response. Now we know that this guy basically determines the decay of the cosine response. of the to the impulse input. So now we can define that since this is a cos, so we can basically find the time period where each cosine oscillation is being completed, right? I know it's not exactly a cosine, but you get the idea, right? So what we can now observe is that if we just substitute the value, we get omega naught by 2q times nt. Now, if q is much larger than half for this particular circuit, what we'll get is that we can just replace omega t by so we can just replace you can just do some substitutions, and from that we can just get that this term will just be equivalent to e minus n pi divided by q, right? So we can just easily converge to this. How I did that is that I just said that omega naught, see, this t is equals to 2 pi by omega t, right? Because this term is oscillating with omega t. But for when q is large enough, this omega t basically is equals to omega naught, right? That's how we express this t as 2y omega naught, and thus thus cancellations happen, and this is what we are left with. Now, if we are able to count the number of complete oscillations, then we can establish the value of the Q factor also. So what we have to do basically is that when e to the power minus n by n pi times q is written over here. So when q is equals to n, this term is basically e minus pi. So term, when the oscillations degrade to 4% of their initial value, so basically this cos wave is starting here. I just should keep it correct. I should just write it correctly only. So a complete oscillation would have happened here, right? And this t is equals to 2 pi by omega t. So this from of this initial value, when the oscillation will degrade down to 4%, at that particular point of time, we can say that this quality factor is equals to n, where n is the number of oscillations that have happened. But again, we should understand that this is true only when q is much larger than half. So by this, just by looking at the impulse response of the circuit, you can actually tell the q factor, which just happens to be equal to the number of oscillations the circuit took to the output took to degrade down to 4% of its initial value. So from this, we can actually comment on the Q factor also. Cool. Now, moving on to uh, next discussion. So I'll just see what other discussion is left here. So again, in a RLC circuit for half cycle, C stores energy, and for the half cycle, L stores. So I think all these things we know. It is basically the statement for LC circuit, where LC are basically involved. Now, this is a second order low pass. These are second order low pass circuits, and these are second order high pass circuits. Again, uh, you can easily understand that how these came about, these characteristic equations. So I'll not really delve into them much for time being. It is just out there. It's not that hard to understand. So we'll just address more things that I have written for myself. So here again, I have just written a general homogeneous second order equation. So I know that its solution is this. So we have already discussed it actually. So now this S1 and S2 is basically determined. This basically determines the nature of the solution. So we know that if the roots are real, that basically implies that the damping factor is more than one, right? Because then we'll just have some decaying terms. But if the roots are imaginary, or the roots are complex, then we know that the damping factor is less than one, and there will be some oscillation because there will be some j omega terms, right? And if the damping factor is zero, then these are just pure imaginary numbers, which means there will be just simple pure oscillations without any decay. That is something that we already understand. Now, here I have basically laid out an example is that I have a circuit given over here where the capacitor is initially charged to this particular voltage and it is now suddenly connected to a RL network. So this is the differential equation for this circuit, the homogeneous differential equation, and this is basically the solution of it. Again, the system behavior, since here no particular input is present, so here we can just simply write the output current as this guy, and now just by applying some initial conditions, we can obtain this graph, right? Because it is just in the end, it is just this only, right? And again, the values of the R, L, and C collectively determine that what is the nature of the roots and how the graph will look like. So this is just one of the possibilities. Yeah. So this is what I intended to discuss. So again, the point is that intuition must not be just some random trick that we have memorized, right? Like we should always be in touch with what is happening in reality in the physics, and also we should be good with our maths. That if in a normal mathematical scenario, how do we have dealt with this scenario? Because in maths, normal maths, when you're solving differential equations, we apply boundary conditions to basically converge to a solution. Those boundary conditions only are the physics, right? Because those boundary conditions give us an essence of what is basically happening physically with these variables. So I guess, yeah, so this basically wraps up the discussion for second order circuits. So there are some things left here and there, maybe we'll discuss them more cumulatively towards the end. Now, in the later videos, what I want to be doing is I just want to briefly talk about some network concepts and some system level op-amp circuits. And then finally, I just want to discuss some questions that I have compiled. Okay, so that's it for time being. And if anyone is watching, thanks for watching. And maybe I'll see you in the next video. Thanks.